Okay, I am recording. All right, let me in my camera. Back here. Close that. Okay, so the first thing we have to do is notice that all the labs that you guys do for 121 are exactly the same, well, almost exactly the same as what they do for 133. This is particularly evident or important for this week because our lab manual sucks. It's okay. It's a lot of the same info is there, but there are a few key things that are missing. So if you scroll down to ours, I'll open this in a new tab. So that's the one we're using, right? Looks like this: conservation of energy. Blah 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 blah. One key thing that is missing is an extension of this equation, or really what it means. This is, of course, a true equation. It's the conservation of energy. That when a process happens, if a process is acted on by what's called a conservative force. So like friction is an example of something that's not a conservative force because it dissipates energy away from things that we would like it to do. This is that, and it's kind of written stupidly as well. It should read E final equals E initial. So that means that whatever energy you start with, the total energy is the same all the time. But another way to write this, so we'll go back to our 121 page, scroll all the way up to the top and click on 133 instead. You'll notice that a lot of these labs look almost identical. They didn't do geometry. They did do the pendulum. What else did they do? They didn't do centripetal force, and they do ideal gas at the end. So let's go to their version of this. And you can see already that there's a picture, which for some reason ours is lacking. Although this picture is kind of crappy, it's so like zoomed away. It's fine, but I would recommend, and you could use it if you cite this, but you can also just take a picture. And like this is what I mean when I say like cell phone picture with like little labels. You can do this yourself, right? You take a cell phone picture and then open PowerPoint or something, and then just add little text box. But something important in this lab that they don't have in the other one is this. So what does this say? This says that energy with time, so this says like if energy is some quantity, it is not dependent on time. That means the derivative of E with respect to T is 0. I'll get back to why this is important as I start running through all these equations up here. But I just want to point out what the differences are so you can use them. Also, one other point that is not, for some reason, mentioned in the R lab manual is the uncertainty of the hanging mass. It is right here. I don't know why we are missing it. Let's see, what is this thing? I don't know what that is. It's some, I don't know, the manufacturer of whatever these little weights are that we're using. Okay, anyway, so if you can see here, we do not have that information, which is really annoying. And you know, a lot of people were asking like, what is the uncertainty for that? Because you need it. So it's annoying that they don't have it. It would go right here. Okay, anyway, let's get to explaining some of these things, these equations, and why this equation is much more important than this equation. They are identical. They say the exact same thing, but this doesn't tell you anything about what to graph, whereas this does. And I'll explain why in a second. Okay, let's go out of here. That's not what I want. I want images. Good, okay. This thing, that's just uncertainties, not really, I'll show you in my lab, in my Google Sheet, it's the same information. Okay, now the first one, I think that's a bit easier, which is just, actually, I think it's easier to start with the harder one. So potential energy. Potential energy is kind of a little bit more mysterious than kinetic. Kinetic's the one that we kind of is always associated with motion, and so it's easier for us to understand that something moving has energy. But potential energy is kind of a little bit more difficult to understand. And actually, one cool aspect of it is that it's really it's like our version or the Newton version. Like, Newton was the one who, apples fell from trees, and he came up with all these laws that we use, like F equals ma, and all those kinematic equations for collisions and how things move through air. Einstein was the one who came at it from a completely different direction, which was entirely mathematical. So Einstein's whole theory of general relativity is all about geometry. And the famous thing that almost everyone knows about Einstein is E equals mc squared. That says that just because something has mass, so this little thing that I'm holding, because it has mass, it necessarily has energy. So just because it's not moving, I could, if I wanted to, throw it really quick and smash it against the wall or whatever. So it has the potential to become energy. So mass, and at the level that Einstein was thinking about things, if they go fast enough, like when you collide things in a giant collider, its mass can legitimately turn into energy, like light energy and heat energy and all sorts of things like that. So our version of that is that just because an object has mass, and so necessarily it's acted on by gravity. So for instance, let's say I define my desk as the origin. And when I say origin, that's kind of also what I mean by sea level here. I'm not sure exactly why I said sea level. It's just the first word that came to my head. If this is sea level or the origin or what some arbitrary point, and I'll explain what that means in terms of our lab in a second, this object right here has no potential energy because it is at the origin. And so there is no gravitational force pushing on it. If, however, I lift it above the origin or sea level, now it has some potential energy. Even though it's not moving, I'm holding it right here. If I were to let go, it would turn into kinetic energy. So the potential for motion is called potential energy. And we write this mathematically as the mass of this hanging thing, the acceleration due to gravity, so that would be like the force with like m times a or m times g, that's the force of this thing falling downwards. And then we know by that thing called the work energy equivalence or work energy theorem, if we multiply a force by a distance, that's work. Let me pull up another thing. It's actually over here. If we know that work is force and distance, so the units of work are force and distance, that means we know the units of energy are force and distance because of this, what's called the work. There's an exact name for it, I can't remember. Work energy, is it just called the work energy theorem? Wikipedia. Yep, just work energy theorem. Okay. So that says that the work is the same thing as energy. So the amount of work that you do changes the amount of energy the system has. So the only thing left, if I know that I have a force, I have m and I have the acceleration downwards, the only thing left is the distance. So this height above sea level or above the origin or whatever, if I multiply that by the force, I get a work or an energy. And so that explains this formula, potential energy. Other symbols for this that you might see in your textbook or whatever are V or U, or V equals mg h. Mass, acceleration due to gravity, which is negative, so I should in theory have a negative right here, and the height. Or you can say that your height is negative because it's going downwards, whatever. The easier one is just the formula that we kind of either are given or we derive. We can derive it by F equals ma, right? If we take the derivative of this with respect to time, what in here is what of value in here is dependent on time, that is the velocity. So if I take the derivative, the 2 comes down, and this equation just says force is equal to ma. Anyway, so that explains the 1/2. That's something I forgot to mention yesterday. But anyway, so this is the kinetic, this is the more intuitive one, that when something is moving and it has a speed, it has energy. Let's see, okay, that's done with that one. Now let's move over here and talk about the units, why these things make sense. So I already went over here. I said that work is equal to energy. Work is force times distance. So that means energy is force times distance. Force is ma. Distance is This m is mass, so it's in kilograms. This acceleration is in meters per second squared, and distance is in meters. And so my unit of energy is kilograms meters squared over second squared, and that is what's called a joule. So if I go over here, Wikipedia is the best for this. Joule units, you can see I type it all the time. Joule and Newton units are by far my most Googled things. It's actually already there. I don't need to know why I'm on Wikipedia. Maybe I did it because of this. So what we'll be using today, usually I always tell people in lab, I don't care what your units are, because usually we'll be plotting things in terms of just whatever unit system we use. And so it's just a quantity that we care about, not the actual units. But today we do need to care about units, because otherwise this equation will be very hard to show or to prove. You can, but it's much easier if you do things in SI units. So that means converting any of the masses that you have, which are given to you in grams, you convert them to kilograms, and any distances you convert to meters. So meters, let's see what else we have. Meters is distance, time is still seconds. Meter length, kilogram mass. We don't deal with that here. We don't deal with that here. Yeah, that's all like thermodynamics, chemistry, electromagnetism, which will be in, if you take 122, that's, is that the second? I imagine that's what the next one's called. Anyway, let's head back over here. So now we have these two equations. What do these mean in terms, I should do the units for the other ones too. Potential energy is mass, acceleration due to gravity, and height. Mass, acceleration, ms squared. M, add those all together, we have kg, kilograms, meters squared, second squared. Same thing over here, although 1/2 is just a number, so that doesn't have a unit. Mass, kg, and then meters per second, all of it squared. So I square the top and I square the bottom. And each of those things is equal to energy. So the units of both of these things is energy, joules. Okay, this we'll do in a second. What's this? That is not super important. What is this? Okay, let's go to this figure over here. One neat thing that we're going to do is we are not going to be measuring this. Actually, it's kind of nice to do without the air on, just so I can show you what I'm talking about. Because the track won't move if the air is on. Hang this over the track, and I hang my mass from it, which you still can't really see. And so whenever, let's just say my string was much, much shorter, and this all the way down here was like, that was my string. So I am going to define this, wherever this mass is hanging, when the part gets all the way down to the end of it like that, I'm going to define that as my sea level or origin. So at this point, or moreover, the right before the cart hits it. So what you'll see when the air is on, it will slowly start, the mass will fall, and this thing will go really fast right before it hits, and then it will collide and go backwards. So right before it hits, wherever the height of this thing is, that I'm defining as my origin. So once that thing, the mass is at the origin, there's no more potential energy. And so all the energy is kinetic. It's right here in this moving thing. However, when the system is getting ready, this string is way too long. Let me try, oh no, it's using this one. Anyway, when this thing is sitting right here, everything is kinetic. So if the air track were on, I wouldn't be able to do this right now. It would be moving. But you kind of hold your hand on here until you're ready to collect on Nagatro. But right now, everything is potential energy because there's no motion happening, but there's potential for motion because this thing is hanging not where it wants to be. It wants to be at the origin, or wherever we define as the origin. So right now, everything is potential energy. But if we notice, this mass is connected to that glider by an exact string. So when this thing goes down a centimeter, that thing moves a centimeter. More centimeters, another centimeter. And so every movement of this, which is a change in height, so we can, instead of using the change in height of this thing, it's exactly equal to how far this thing moves. And so if you see at the top of your tracks, there's another picket fence. So just a reminder, let's go back to lab 2, where remember the picket fence was like, you take a blank, like a clear segment and a dark segment, and that's your segment. Yeah, right. I already messed it up. Clear and a blank part, and you add those together, and so it's a segment. Actually, let me just pull it up, because as I'm remembering, there's actually not a good picture in that lab report or in that lab manual anyway. So let me go over here, go to acceleration lab, and try to find a picket fence picture. There we go. Perfect. Yeah, so this is exactly what we have at the top of our system. And so if you see, when I pull this cart right here, you'll see there's a flashing light happening, because the blue or red thing on the top of each of your carts is a photo gate. And so when it gets a dark spot, it says, oh, I'm blocked, I'm not blocked, oh, I'm blocked, I'm not blocked. And so you're getting the exact same information as lab 2. And remember just to count things like this. So it's like one full one is a blank and a dark one, blank and dark one, blank and dark one. And you just measure some number of them. It can be 7, it can be 10, whatever. You measure the distance, d, and you divide to get the small d. And again, this is our conversion factor. So that multiplied by segments is a length. That multiplied by segments per second is a velocity. So for instance, all of this stuff is from Logger Pro, all this yellow stuff. And then to get to physical and physical, you just multiply each of these columns by your conversion factor d. And so that's what you're seeing over, no. Let's see, I have a million preview things open. Here, okay. So what does this look like? All the important data is the one where you can see 1, 2, 3 bits of information. This one's not that important because we don't have a velocity yet. It's the first one. So let me, I don't know why I can't highlight. There we go. This goes right here. Boop, boop, boop. So you put in your time, your distance, that goes, the distance doesn't matter. You can just label it whatever you want. It's just like if you notice 1, 2, 3, it's just the number of segments that's gone by. So it doesn't, that's all that matters is that it's consecutive. So 2, 3, 4, 5, 1, 2, 3, 4, 5, it doesn't matter. And then velocity is in segments per second. And so we convert it to meters per second by using our little conversion. So all this stuff goes in here. And so I collect this one, I collect this one. So yeah, I shouldn't be clicking and dragging all the time. I collect this one, I collect this one, this one, this one, and this one. Ideally, you would have enough trial. So if your string isn't long enough, you won't get enough information. Ideally, have at least like, I don't know, at least 6. How much is this? This is, yeah, so this is kind of like the bare minimum. I barely got a good answer. But so if you get like 5 measurements or less, I would say like tie it, like grab someone else's longer string. This one's huge. So you can just take a pair of scissors and cut it and make yourself a longer string. Okay, so that's what that means. What's over here? Okay, so head back to the thing. And what are we going to try to prove? So we are going to do so the initial system, everything is potential energy, and the final system, everything is kinetic energy. All of the like in between times is a mixture. So it starts completely potential, ends completely kinetic, but in between it's a mixture of those two. Regardless of that, the energy, because the energy is conserved, that's a law of physics, that in the absence of external forces. So for instance, that's why we have the air track. If we didn't have the air track, there'd be friction, which would not be, like friction would not be conserved there, unless we had some way to measure friction, which is incredibly hard. But anyway, one other point to mention is that the potential energy only comes from this thing, because that's the only thing being exerted by gravity. This thing, like it's the, like, sure, this thing has gravity working on it, but this is the force that's acting downwards. So the potential energy is just the hanging mass, whereas the kinetic energy, because these things are tied together with a string, the mass that we use for that one is both of them, so the total mass, hanging mass and part mass. Anyway, so what does this mean, and why is it a crappy equation to use, and we use this one instead? An example of what this equation means is kind of like, what does it mean for something to not be dependent on? So what if I had E equals 10 E squared? That is not independent of time, because if I take the derivative of it, that one thing, I should just be drawing bigger, I guess. Yeah, bigger. So if I take the derivative of this, the exponent comes down. So I have a 2 times 10 and t. This is not equal 0. So that means this is not equal 0. So this equation right here means that that is not equal to 0. However, if, so another way to say dE dt equals 0 is to say E not equal a function of time. So this means it's some, that's kind of on there. That means like not that. That is a function of time. So I can really say that as E of t, like f of x, the function. Because if I plug in another value of t, it's a different value. But if my equation were this, the derivative of something that doesn't depend on it is 0, because there is no t there. So it's like t to the 0. And now if I bring it, if I do the derivative of this, the exponent that comes down, like this doesn't even matter. Sure, it's if I follow the rules exactly, this you lower the exponent up there, but there's a 0, so this doesn't matter. It's just equal to 0. Now, why is this a much more approachable equation for what we're doing in class today? Because I can interpret this if I wanted to graph something. Rise over run. Or another way to say that is I can multiply both of these by dt so that this goes away from the denominator and this is dt. So, as we almost always do in the class, so this tells me if I plot the energy, the total energy on the y-axis, and I plot the time on the x-axis, my slope should be 0. So that means our expected result of this lab today is that the slope of E and T is 0. It won't be, but it should be very close, like 0.0000 or negative 0.0001 or whatever. So I think that should be it. Anything else fancy in here? No. Okay, so I will turn the air back on and you can start playing air hockey. Also, for some reason, the discussion questions on this are just awful. So the discussion question will be from the other one. Where are we? Okay, 1, 2, 3. So instead of just plotting dE over dt, there's one discussion question down here that's really nice. It's very easy. This one, which is to plot. Oh, why can't I highlight this? Trackpad sucks. Anyways, this one. It just says to make a plot of KE. Oh, it's actually kind of worded crappily. Yeah, I'll word this better. Or I'll just work on it while I'm over here. But what I meant was like to plot P, like make this equation KE over T and PE over T. And plot those graphs on the same plot and look what they look like. It's very easy. It's an equally viable way to see this equation. Okay, I'll write that better in the announcement. Okay, escape, stop share, and start recording.